So we're going to be talking today about what a number is. So we're going to be specifically focusing, a lot of this is going to be pretty basic stuff, but we're going to try to examine it in the context of thinking like a mathematician and thinking about abstraction, how you put together different ideas, things of that sort. So, but first, before we talk about what a number is, I want to talk about who are you. So we already went through some of what you guys are studying, A, B, C, or D. Let me reset the, if you haven't done that, you can throw that in, but I'm going to go ahead and reset the poll, and now I'm going to ask you, what year of university study are you in? Are you a first year, second, third, fourth, 5+? So throw that in chat and just get a sense of. So normally I try to get this, have all you guys talk to each other briefly and get to know who else is in the class, but of course that isn't as possible, so we're going to do this all via a poll. So it looks like we have a lot of first years and a few second, third, fourth, or fifth years. So if I were answering this, I would have to answer E because I am well beyond my fifth year of university study. Oh, and I guess I didn't mention. So what am I studying? Well, I'm William, so you can call me Prof. U, Professor U, and I'm in the math department, but the stuff I do actually relates very much to computational biology. So this is the kind of work that I do in my professional life. But back in undergrad, I actually did study language as well. So I was a Germanic studies major. So read a lot of German literature, but then decided to be a mathematician professionally. So I did chemistry, math, and German back in undergrad, so I have some affinity towards the language arts as well. Okay, so let's see, we have a lot of first years, a couple second, third, fourth, and fifth years. Okay, and I think I already mentioned earlier on that if you have questions, you can always bump up the confusion meter, and that will show up as well. So I will be periodically watching the chat as well as my confusion meter, and if lots of people are getting confused about some topic, that is my sign to slow down. One other thing I should mention is that I go really fast, so you might have noticed that I speak quickly, and I only really slow down if you ask questions. So please ask questions because they'll slow me down and keep me from zooming on ahead. Okay, so now that we've done that, let's go ahead and ask another, let's ask some math history questions. So, if we post multiple question marks, will the meter be bumped more? Yes, it will. For the record, it will be bumped logarithmically with the number of question marks you put, and it'll be summed with the total number of people who are putting, it's some weird logarithmic formula. I can send you the formula if you want later, but for now, let's ask a quick question. So, now, when we talk about numbers, you guys have probably heard about all kinds of numbers. Real numbers, imaginary numbers, complex numbers, whole numbers, natural numbers. So now, when were negative numbers invented? So, like, you might think, like, well, are negative numbers a real thing? Are numbers real? Like, what does it mean? Does the number 1 really exist? Are you a Platonist? Are you a Neoplatonist? Do you believe that mathematics really exists? Or is it some fiction that mathematicians have dreamed up? And so I'm not going to answer that philosophical question because that's the sort of question that a philosophy of math class would go into a little bit more, or an epistemology class if you're more into philosophy. But now, a lot of people are, but now it turns out that negative numbers are one of those confusing things that we all learn in grade school. But then there's the question of, like, when did humanity as a whole come up with the idea of writing down negative numbers? And so let's see, what are our class votes? So there we have a decent number of people, so it seems pretty split. People seem to really think they're either really, really old. They're obvious, right? Negative numbers, like if you have positive numbers, then of course you can have negative numbers, right? On the other hand, we have people who are like, well, negative numbers are really, really complex, like, and they probably were invented only after 1800 in the current era, so only the last several hundred years. And, well, the answer is actually that they were invented between 200 BCE and 220 CE during by the first recorded instance of people writing down negative numbers are these counting rods that, which is a numeral system that the Chinese had back back during the time period between 200 and BCE and 200 CE. And here I've given you an example of these counting rods. If you're interested in this, I'm not going to go into too much detail on how exactly the format of these works. You can sort of look at it. It has these sorts of horizontal lines for some, and vertical lines for some numbers, horizontal lines for other numbers. And there's this notation that allows you to write down pretty big numbers. And the Chinese were using this notation to keep track of numbers, for a very long time. Was the concept of negative numbers widely used back then? So that's exactly the sort of point I'm getting at, is that negative numbers, before this time period, no one had been writing down negative numbers. In fact, there was, I forget which Greek mathematician it was, but there was some Greek mathematician, I should really look these things up, maybe I'll look it up for the next class, who said something to the effect that an equation that had a negative number as a solution was nonsensical. What does a negative number mean? And that gets back to what we mean when we talk about math. So what is the point of numbers? And now, some of you who like math a little bit less might be like, well, numbers are here to confuse people. But that's really not the case. Numbers are here to try to encapsulate concepts that humanity cares about. And one of those concepts is counting, which we'll get to in a little bit. And so if you're counting, say, the number of apples that you have in a bushel, well, you can't have negative apples in the bushel. And so the concept of negative numbers wasn't a widespread thing. And so somehow it took until around 200 BCE before someone had the idea of like writing down negative numbers and using them. Another thing to notice, so also notice, 0 wasn't invented yet either. So 0, the concept of just like nothingness. Well, the concept of nothingness has been around for a very long time, but the idea that it ought to be a number, that took much longer for people to figure out. So you notice here that normally, if we were writing this number 5089, we would put something like a 0 here. So we have 5 lines here, 0. This number corresponds to an 8, and this corresponds to 9. But we don't actually have. They didn't actually have a symbol for the quantity 0 here, even though they clearly had some sense that there was something missing. And now this sort of example, this sort of history lesson, gets back to one of the basic ideas of the questions we're going to be exploring in MATA02. So, what is a number? Like, why do we use them? What is its relationship to things like counting and measurements? What are common operations on numbers? So, you guys obviously have heard of addition, subtraction, multiplication, division, exponentiation, and roots. But where do those ideas come from? And why did mathematicians either invent them or discover them, depending on what philosophy of math you subscribe to? Other things we're going to explore in this class. Well, can we extend what it means to be a number? So if you think about what we're talking about, like if negative numbers were invented, that means that at some point we didn't think of negative numbers as corresponding to some property that we cared about. Or we just didn't think to extend numbers to correspond to that. So we'll talk a little bit more about how mathematicians have extended the idea of what numbers are. So you can extend the numbers, you can add real and complex numbers, so you can add imaginary numbers to the mix. But you can also extend them in other ways. So you can use these ideas of things that look like numbers but have slightly different properties, and it turns out those can correspond to real life concepts that we care about, such as something we'll talk about later, clock arithmetic. Next, we're going to be talking about what's so special about prime numbers. So you guys have probably heard of these. These are just numbers that are only divisible by 1 in themselves. So how many of those are there? Can we find where they are? Why are they so special? And lastly, these prime numbers are one of the most magical things about number theory and mathematics. And it turns out that we have to use them in our everyday lives. The magic of prime numbers is why the online security, online encryption that we use works. So, the sort of payoff to this class we'll be talking about, we will sort of be building up by thinking really hard about these ideas of what numbers are, and we'll eventually end up with how prime numbers are used in online security. So we'll show you how people apply these sort of esoteric things in number theory to actually change stuff that to use things that we use every day. So like whenever your phone is connecting to your email server, it's going to be talking to the server using prime numbers, and that's part of what makes this branch of mathematics so cool. is these kinds of applications. But the fact that these applications are there isn't part of the sort of joy of numbers. What we're going to be trying to be doing in this class is exploring these ideas and teaching you how to think like a mathematician. And this is going to be slightly different from some of the other math classes you've taken, because often in math classes, we sort of treat it like a cookbook. We teach you a bunch of algorithms. So this is how you multiply numbers. Memorize your multiplication tables, and then you're going to use them, memorize the quadratic formula, then you apply it, and you get some magic answer. But those magic answers have to be ones that someone came up with once upon a time. And in this class, we're going to explore how you might think like the people who came up with those sorts of ideas. There's a chat. Yes, yeah. So there's a chat about the pre-lecture notes. I have posted the pre-lecture notes already. I will also post the post-lecture notes afterwards, especially if I do a lot of writing. Since on some of these things I've left blanks, I will also post the post-lecture notes afterwards. Okay, but so now that we've talked about the sort of overall philosophy of what numbers are, well, let's take a step back and let's start going back all the way to like when people first started using numbers. So one of the first things people use numbers for is counting, right? So you might count, how many apples do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. So I unfortunately am not a very good artist. I'm sure many of you are much better than I am. So I'm going to draw these as stars instead. So let's say 1, 2, 3, 4, 5 stars. Okay, so I can count 5 stars. Well, another thing I could do is, well, maybe I have circles. Let's say I count 1, 2, 3, 4, 5 circles. Excuse me. Too much talking early in the morning. So I can count 5 stars and I can count 5 circles. And somehow, even though stars are not the same thing as circles, there's some underlying concept that both of these represent the concept 5. And noticing the similarity and then formalizing it, like giving a symbol to this. So this seems obvious to us now, but the idea that 5 stars and 5 circles have something in common is one of the sort of early inventions of counting and numbers and why these things, and then you can use that abstraction to do other things. So these are what we call the natural numbers, because they sort of arise naturally out of this idea of counting. Note that 0 is a late addition to the natural numbers, since it took mathematicians a lot longer to figure out that it needed a name. So like, if you start thinking about natural numbers just coming from groups of objects, so I have a collection of 5 stars here, I have a collection of 5 circles here, well, you don't really have can you have a collection of 0 stars? Well, now that we've given it a name, we can say yes, well that means you have no stars. But it sort of isn't quite as intuitive because it's not quite the same kind of thing. Well, we also have some other questions. So, for example, what about negative numbers? Are they natural? Before you post, so whenever I ask questions, you need to wait until I type reset into the chat, or it won't work. So now, I'm just going to ask you guys, are the negative numbers natural? So this also gets back to, note that I put natural in quotes, because, well, what does it mean for something to be natural? Okay, so a lot of people are split between A and B. A couple of people also are saying that mathematicians are silly and come up with weird arbitrary definitions. For the record, B is absolutely correct. Mathematicians are silly and come up with all kinds of weird arbitrary definitions. But that doesn't change the fact that those weird arbitrary definitions are sometimes quite useful. Okay, so it looks like we're pretty evenly split. Are the negative numbers natural? And so the answer to that really depends on how you define it. So like as a mathematician, what I would say is, well, we haven't defined the term natural, and so it doesn't make sense to ask that question. But I'm sort of asking this in a sort of more intuitive way, and the answer is that negative numbers took people a lot of time to figure out. Like somehow they don't make sense the same way the counting numbers, 1, 2, 3, 4, 5 do. And so many people would argue that negative numbers aren't natural for that reason, but once you see what they can be used for, then you might be like, well, it makes sense that you need these negative numbers for some purpose or another. So negative numbers, well, you can also ask other kinds of questions. So let me, for example, are fractions natural? So is 1/2 a natural number? And let me reset before you guys reply, just so that you can see what people think about negative or fractions. Okay, so I see that we have a mix of A's and B's, but a lot more people seem to think that fractions are natural than negative numbers. And so let's again get to the sort of intuition we have about like objects. So maybe you think, well, yeah, you can have half an apple, or you can have 4/3 of an apple. You just cut it up, and then you have little things like that. But of course, these aren't natural counting numbers, because you can't just count 1, 2, 3, 4, 5. Instead, you're sort of what you're doing is you're taking something, you're dividing into the pieces, and you're counting using natural numbers each of the pieces. And so there's some sense in which fractions also have this sort of weirdness. They're not quite as natural as the counting numbers, but they sort of make sense to us, especially since we've learned all about fractions. Okay, well, let's reset, and let's do one more, please. So what about imaginary numbers? So you guys have probably heard about imaginary numbers. These are things like the square root of -1, which we sometimes call I. Fractions are things like 5/7. Negative numbers are things like -2. So what about imaginary numbers? Are imaginary numbers natural? Okay, so very, very few people are saying, or actually no one so far says that imaginary numbers are natural. And that sort of makes sense, right? That's part of why we've named it that. Like, imaginary numbers actually took a really long time before mathematicians really sort of got the hang of them, like up until like the Renaissance period in Europe, when we came up with the idea of imaginary numbers to solve cubic equations. But somehow, imaginary numbers, like, they don't seem very natural, but mathematicians have still managed to figure out how to use them, and they're actually quite important for things like electromagnetism and understanding how those things behave. Okay. But anyway, there isn't really a right or wrong answer to these quiz questions, chat questions. I just wanted to get you to start thinking about the idea of what does it mean for a number to make sense? Does the number make sense just because you can use it for something? Or does it have to correspond to some natural concept? Does it have to be something you can use to count? Like, how do you count imaginary numbers? So clearly, imaginary numbers and fractions are negative numbers. They don't quite have the same sense of counting that the natural counting numbers do. Okay, now we've done that, let's move on. We're going to invent addition. So now, we've learned how to count, right? So let's assume that we all know how to count. Well, one thing you might do is you might be like, well, if I counted one group of objects and if I counted another group of objects, how do we figure out how many total objects there are if we put the items together? So maybe we have, let's say, 5 boxes here and 3 boxes here. Well, how many total boxes do we have? Well, now one thing we can do is we can count. So we count, this one is 1, 2, 3, 4, 5. And if we count this one, that's 1, 2, 3. Well, we can count both of them together, and we get 1, 2, 3, 4, 5, 6, 7, 8. Okay, great. So now that gives us a way of counting the 2 different groups of objects and putting them together. But of course, that's sort of slow, right? Because you have to recount the entire set of objects over and over again. But one thing you might notice is that it doesn't matter what objects you're counting. So if you have circles instead of boxes, if you count those, well, you have 5 circles, you have another 3 circles. You count those together, you again get 8. And now, we're not going to go through too formally and prove that whenever you count objects of different kinds that they're the same. Like, that's a totally different type of question, but you can sort of, and requires actually a lot of formalism to like make precise what we mean by that. But what we care about here is that putting together 5 squares and 3 squares gives 8 squares. And at the same time, we also know that putting together 5 circles and 3 circles gives 8 circles. So the type of object that we are counting doesn't make a difference when we're putting them together. And this, so once you've done this, then you might think, well, what does this have to do? Like, what can we do with this? Well, we have to think like a mathematician. Have I seen this problem before? So when you see the problem of counting these groups of circles, combining these two groups of circles together, well, you have seen that problem before. Like you can reframe. You can reframe the problem. You can reduce the problem to a previously solved problem by saying, oh, well, counting circles and counting squares is the same. And so one thing you might do is, well, what if you now know that counting circles and counting squares are the same? Well, maybe you might have the idea that counting any set of objects is the same. So somehow counting is abstracted away from what it is you're counting. And then once you do that, well, then you might consider creating a table that lets you look up, putting together two numbers, so you don't have to count 1, 2, 3, 4, 5, 6, 7, 8 each time. And that's something we can do. So I'm going to go ahead and put 0 in there. So if you have one group that's 1, 2, 3, 4, and you have another group that's 0, 1, 2, 3, 4, you can add them together. And so this gives you your addition tables. So for example, if you have one blue box and one red box, that's going to give you 2 once you count there. So that gives you a 2 here. If you add another red box, then that gives you 3, and so on. And so obviously we can write a full addition table, and this is something you probably memorized back in primary school, and so on. And that's one of the things that mathematicians care about, is we figure out that, oh, these two problems are actually the same, and then we write these things down. So once you've solved one problem, once you've counted circles, you don't have to then repeat the entire process and figure out how to count squares again. Once you've reduced a problem to a previously solved problem, your job as a mathematician is done. Well, not quite then, because you might want to figure out how to communicate this to a friend of yours. So how do you write these things down? Well, saying that we want to group together one group of 3 objects and another group of 5 objects is kind of tedious. So what we can do instead is we can invent symbols. So this is why we invented things like the plus sign, where if x and y are arbitrary numbers and we put a plus between them, that means we're counting the total number of objects when we group together a group of x objects and another group of y objects. And then we also have another sign, the equal sign, to denote that two expressions are the same. So 3 plus 5 is equal to 8. This is a very succinct way of sort of capturing the property that if we have 3 blue boxes and 5 green boxes, if we add them together, we have a total of 8 boxes. 3, 4, 5, 6, 7, 8. And once we've invented this notation, you might ask yourself, well, we have this operation of grouping things together. What properties does that have? And these are things that you've probably memorized back in school. So you have things like what the mathematicians call the commutative property. If you group together a group of 5 objects and a group of 3 objects, that's the same as grouping together a group of 3 objects and a group of 5 objects. If this were a upper year, 3rd or 4th year number theory course in the math department, we would actually have to sit down and really formalize this all using mathematical logic. But because this isn't that, this is a 1st year class on sort of just trying to get you the flavor of mathematics, we're not going to prove that, but we're just going to mention that one of the things is, once you have this abstraction, then you might ask, what are the properties you care about? And we get the commutative property out of that. Another is the associative property. So if you have a group of if you put together a group of 1 object with 3 objects first, and then put it together with a group of 5 objects, that's the same number as you put together the group of 3 objects and 5 objects first, and then add another one to it. And because this is true, this means that even though the plus symbol we originally defined as putting together 2 groups of objects, this means that you can use the plus symbol to put together more objects, and without any ambiguity. So you can write 1 plus 3 plus 5. We also have another important property, the identity. It turns out if you take a set of objects, you add nothing to it, then you get the same number of objects back, which hopefully makes sense to you all. So this is so you probably learned all these properties in grade school. Well, what these properties are, they aren't some arbitrary set of rules that we ask you to memorize. I mean, we may have asked you to memorize them at some point, but they're not just that. What they are is, they're the natural thing that comes out of defining addition by grouping together groups of objects. So what we're doing is we're understanding this operation that we've defined because we care about grouping together groups of objects and seeing how many total we have. There's one other property you guys probably mentioned, probably learned in school, which is the distributive property, but we haven't invented multiplication yet, so we can't talk about the distributive property. So over the course of the probably on Wednesday, since I'm running a little bit out of time, we'll invent multiplication, and once we've done that, then we can talk about these other properties and how they relate to each other. So that was a little bit fast. Does anyone have any questions about what I mean by this? So the point I'm trying to get across is that these properties that we guys had you memorize, they're things that naturally arise out of thinking really hard about the operations that we care about. And sometimes you might ask yourself, well, what happens if to numbers if one of these properties is slightly different? And if you ask yourself that question, then you're really thinking like a mathematician. You're asking yourself, what if these properties weren't exactly what they are? And we'll get to that in a moment. So, why is it called a property? Is it like a rule or just a natural occurrence? That's a really good question. So we call it a property because what we've done is we've defined some operation. We're grouping together things. And we're asking, what are traits, what are characteristics of this operation of grouping together objects? And so that's why we call it a property, because it's something that's associated with an operation. So you can think of it like a rule. So it's a rule when you think about manipulating symbols. So you guys probably studied algebra in school. And one of the things you learn is you learn all kinds of rules for how you manipulate things and move them around that are valid. And so when you think about it that way, then you can call them rules. But when you think about them as some characteristic, some trait, or some natural occurrence that happens to be associated with some mathematical idea, in this case, adding things together, then it's really a property of that, and that's why we call it a property. So in the same sense that, let's say I have a pen here, you guys, so it's an electronic pen, but you might say, well, one property of this pen is that it's white. And so, when we say that one property of addition is that it's commutative, that's sort of what we mean. We have this idea of what addition means, and then there are these rules or properties that sort of come out of that idea. There's another way of going about this, which is to define a set of rules, and then assume that those are properties of some operation, and then see what happens. And that's also another part of mathematics. Okay, so let's see if we have time enough to invent subtraction. And then we'll probably have to end for the day. So how do we invent subtraction? So you might ask, well, addition is when you group groups of objects together. What happens when we take objects away? So let's say we have 5 boxes. And then we're just going to take away 2 of them. So notice that if you count, you might count 1, 2, 3, 4, 5. And then you count 1, 2. If you take those away, you're left with 1, 2, 3 boxes. Oh, sorry. Let me write this a little bit further up. So just 1, 2, 3. And so one way of encoding this information is we might use this minus sign. So 5 minus 2 is equal to 3. Note that subtraction doesn't have the properties of subtraction. It doesn't have the commutative property, because if you subtract, you can't take away 5 items from 2, or 3 items from 2, because you don't have enough items. But this is a well-defined operation if you start with more items and you take some of them away, right? So we can create a table like we did for addition. So for example, let's say that we start with 0, 1, 2, 3, 4, and 0, 1, 2, 3. So, what happens if you start with 0 items and you take 0 of them away? Well, then you're left with 0 items. If you have 1 item and you take 0 away, you're left with 1 item. 2 items you take 0 away, you're left with 2, and so on. But then you run into trouble when you have no items and you take 1 away. So what happens when you have 0 apples and I take 1 away? What does that mean? Well, we haven't figured out what this means yet. So that's not a well-defined operation, because if I have 0 apples, you can't take 1 of them away. So that doesn't make sense. But, 1 minus 1 makes sense. So So that's 0, 2 minus 1 is equal to 1, 3 minus 1 is equal to 2, 4 minus 1 is equal to 3, and so on. Then you end up with the same problem again, 0 minus 2. Well, that doesn't make sense. Also, what about 1 minus 2? Well, that also doesn't make sense. But 2 minus 2 is equal to 0, 3 minus 2 is equal to 1, 4 minus 2 is equal to 2, and so on. So note that the table is somehow incomplete because some operations don't give an answer. So it's not defined when we say, well, how do you take away how do you take away 2 items from 1 item? Because you just can't do it, right? If I hand you 5 apples, and then you can't take away 7. Like, you take away 5, and then, well, you're stuck. So, what should we do? Before we answer. So, there are several things we could do. What should we do? It's fine. You can vote. It's fine. We don't need all subtractions to make sense. Or, we could invent some more numbers. Or you could just take the point that, well, all of math is pointless, and it doesn't actually matter what it is, because it's also a meaningless set of games. Okay, so it looks like most people are down to invent some new numbers. So you guys are already thinking like mathematicians. Well, we have various operations, and they don't work the way that you expect them to. So you might answer, well, it's fine, we don't need the subtractions to make sense. We don't need all subtractions to make sense. And that was the position of humanity for thousands of years. For thousands of years, we did not need negative numbers because you would never take away 7 apples from 5 apples. That just wasn't something you would do. But of course, mathematicians aren't content with that, and so at some point, they decided to invent some new numbers. And of course, there are some people who have always thought that math is pointless. I am not one of them, and I hope by the end of this course, well, I can convince you that math is not pointless. But of course, that is a position you can take. But let's invent some new numbers, and we're going to call them negative numbers. So you guys have already seen these, which is why we're giving them these names. Whenever mathematicians invent new numbers, they do have to give them names, and sometimes the names, you have to play around with them a little bit before they stick. So, what if we double all the natural numbers? So we have the natural numbers 1, 2, 3, 4, 5, or maybe starting from 0. What if we double all of them and put a minus sign in front of the copies? So what do we mean by that? Well, you might say, well, we have 0 to start off with. And let's say 1, 2, 3, 4, and so on. And let's put this in a different color. Let's say minus 1, minus 2, minus 3, minus 4, and so on. So what we've done is we've made a copy of all these numbers and just put a minus sign in front of them. So the left copy of numbers we can refer to as negative numbers. And once we've done this, we can notice that subtraction x minus y is well defined when x is greater than y. And what we can do is we can say, well, if y minus x, where x is greater than y, well, that's not well defined originally, but we can just say that it's equal to minus of x minus y. And so I'm sure you guys have seen this. So then 3 minus 5 is equal to minus 5 minus 3, which is equal to minus 2. Or 0 minus 7 is just equal to minus 7. And this is one of the reasons why we use the same symbol for minus and negative, is because you can just sort of drop the 0 in front of it, and it means the same thing. Okay. And let me end on one last question to you guys, and we're not quite going to finish. Actually, we should. Okay, we're going to run a little bit out of time, but we'll come back to it next time. So, what problem remains after having invented negative numbers? So, is it that we don't know how to subtract negative numbers? We don't know how to add negative numbers? We don't know how addition and subtraction interact? All of the above or none of the above? Okay, so I'll admit, that's a little bit of a leading question. But the answer here is, yeah, we don't know how all of the above. We haven't defined what it means to subtract negative numbers. We don't know how to add negative numbers. We don't know how addition and subtraction interact. Because we're in the process. So you guys know how to do this already because you guys have already taken school and we've taught you these things. But we're here inventing. We're here inventing numbers. And when we're here inventing numbers, we haven't invented or we haven't defined these various other operations yet. And that is where I'll leave you off for today. When we come back on Wednesday, we'll talk a little bit about the number line and how that's one way of thinking about addition and subtraction. And then on Wednesday, we'll also talk about other operations. So we'll invent multiplication and division and so on, and really just get at the heart of what it means to think like a mathematician about numbers. With that, thank you all very much. I do have time to stick around for a little bit after class today, and I will stop recording now.